So the total change theorem is actually one of my favorite concepts in calculus. And I think the reason is because I remembered that I was when I went through calculus, I was white knuckling it the whole way. I was barely hanging on when I learned calculus for the first time, which I think you guys are doing a lot better than I am the first time I learned calculus. But it was when I got to the total change theorem that things really started to click and make sense for me, and conceptually, I felt like I had a pretty firm grasp onto what was happening. So let's just go through this checklist, and I'm going to go kind of fast through it, but you stop and pause the video to make sure that every one of these statements makes sense to you. Okay, for statement number 1. If you have a moving object with an instantaneous velocity, v of t, the object's change in position on the time interval from a to b is given by the definite integral from a to b of v of t dt. Make sure that makes sense. And whenever velocity is positive on the interval, v of t also tells us the total distance traveled by the object on that interval. Pause, make some sense out of that statement. If that doesn't make sense, you're going to reach out to your teacher and get some clarification on that. Here's a second interpretation of the definite integral. If you have a continuous function, the definite integral from a to b of f of x dx represents the net signed area bounded by y equals f of x and the x-axis on the interval from a to b. There are going to be some regions that lie below the x-axis, and those regions have a minus sign associated with their area. Again, if that doesn't make sense at this point in time, you need to be reaching out to your teacher to get some clarification. And the third and final interpretation of the definite integral. The value of the definite integral is directly linked to the average value of a function. Average value is a little misleading. I think it's the average output of a function, right? A function is going to give you infinitely many outputs on some interval from a to b. The average output on a continuous function from a to b can be found by taking the definite integral from a to b of f of x dx and then dividing that integral, dividing that value by the distance along the x-axis, b minus a. Okay, or we say 1 over b minus a times the definite integral of a to b of f of x dx. Now, we have not done a lot of work with this yet. We kind of just threw this at you. We did maybe one problem with it and said, look, it works. But we're going to be doing more with it now. Okay, now, fundamental theorem of calculus, or the FTC, as we call it in the biz. If we have a velocity function, then the definite integral from a to b of v of t dt is going to be exactly the same as the antiderivative of the velocity function evaluated at b minus the antiderivative of the velocity function evaluated at a. You can think of this here as being velocity. This is now position. All right. If we replace v with s, which is kind of where I was headed with this, represents position, and we replace little v with s prime, because velocity is the derivative of position. So s prime is exactly the same as v. Then we got this statement right here. And this statement should make sense to you. And again, if this isn't making sense, you got to reach out to your teacher, because this is stuff that you should understand by now. So the fundamental theorem of calculus tells us the total change in an object's position function on a particular interval, also known as displacement. And it's given by the definite integral of the position function's derivative on that interval. Okay, so there's your checklist of things that should make sense. This video is definitely going to go over 5 minutes. So if you need to take a break, take a little break, go get a drink of water, come back, and now let's do the total change theorem. If f is a continuously differentiable function, it's continuous and differentiable on the interval from a to b with the derivative f prime, okay, then we can say that the original function, f of b minus f of a, is equivalent to the definite integral from a to b of f prime of x dx. And again, we can get away with saying this because we know, what we know is that f prime, I should say f, circle over here, f prime is the derivative of f. All right, that is, the definite integral of the rate of change of a function a to b is the total change of the function itself on a to b. Now, you might have a little bit of a hard time making sense of this. Theorems are sometimes a little bit difficult to make sense of, but let's see if we can put this into context for you. So this picture is going to do an excellent job at explaining the total change theorem. So let's see what we're dealing with here. On the left, we have f prime of x. On the right, we have f of x. Okay, so this should make sense that f of x is a quadratic. So f prime is going to be 1 degree less, so it's linear. Okay, the f prime of x is a linear function 4 minus 2x, f of x 4x minus x squared. What this says is that the differences in heights of f, that's this function here, correspond to the net signed areas bounded by f. In other words, if I take let's take the interval from 0 to 1. What's the difference in height? Well, the difference in height is going to be 3 minus 0. That's 3. That corresponds to the area under the derivative curve from 0 to 1. What's the difference in height from 1 to 2? Well, the difference in height, all right, the difference in outputs, 4 minus 3, which is 1. That corresponds to this little area right here from 1 to 2, the area under the derivative function. How about from 2 to 3, on the interval from 2 to 3? Well, now the difference in heights is negative 1. 3 minus 4 is negative 1. So that's why it's under the curve here. And the difference in height on the interval from 3 to 4, that's going to be negative 3. 0 minus 3 is negative 3, right? It's decreasing. And that's why 3 is represented under the x-axis here. So that's what the total change theorem says. Maybe go back and read the total change theorem again. Make some sense out of that. Okay, so in using notation, we can say f of 1 minus f of 0. Okay, think about that. F is the original function. F of 1, which is 3, minus f of 0, which is 0, is equivalent to the definite integral from 0 to 1 of f prime of x dx. And both of those are equal to 3. So now you're seeing a very strong connection between a function, its derivative, the change in outputs versus the area under the curve. All of these things are connected. All right, if you need to take another small break, take another small break. Here is a big example for us to digest. Don't be offended that I read this to you. Suppose that pollutants are leaking out of an underground storage tank at a rate of R of t gallons per day, where t is measured in days. It is conjectured that this rate of pollutants leaking out is given by the formula R of t equals blah, 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 all that. And this is over a certain 12-day period, over the course of 12 days. The graph of R of t is given in the figure. Let's take a look. There's the graph of that function from 0 to 12 days. What is the meaning of the definite integral from 4 to 10 of R of t dt? And what is its value? So 2 questions in one there. Then, what is the average rate at which pollutants are leaving the tank on the time interval from t equals 4 to 10? So pretty loaded example here. So let's go through this step by step. The definite integral from 4 to 10 of R of t dt is the area under the curve on the interval from 4 to 10. Okay, so that's that area there, which we don't have a value for yet. The rectangles will have heights measured in gallons per day and widths in days. So if we think about a number of rectangles being drawn to approximate this area, the height of the rectangle is going to be gallons per day. The width of the rectangle is going to be days. So when we multiply that out, when we multiply height times width, we get gallons per days times days. The days will reduce, and we're left with just gallons. So the area under the curve, that blue area right here, represents gallons. Let R of t, big R of t, denote the total number of gallons of pollutant leaked up to day t. Now, notice that little r of t is measured in gallons per day, so that's a rate. This is a derivative function we're looking at here because it's a rate, gallons per day. So r of t is just going to be gallons. That's the original function. What we know is that the derivative of big R is equal to little r. And we also know that the definite integral from 4 to 10 of r of t dt is big R of 10, the antiderivative of little r, minus big R of 4. Okay, all this should be making sense so far. Using the fundamental theorem of calculus and using the antiderivative of this, using the rules that we talked about in class, it was either Brent's rule or Taylor and Emmy's rule. I can't remember whose rule it was in Mr. Benton's class, but I'm sure we named it after somebody. We can say this: the definite integral from 4 to 10 of this whole function right here is going to be equivalent to, here's my leading coefficient, divided by 4. Where do we get the 4 from? Because we added 3 plus 1, t to the 4th. Then we take 2 plus 1, which is 3. We take 0.125 divided by 3, t cubed. And then we take 11.079 t, and we're evaluating that from 4 to 10. So we're going to plug 10 in for t, boom, which we're not showing that work. Then we're going to subtract, then we're going to plug 4 in for t, which we're not showing, and then we're going to subtract the 2. And when we do that, or if this would be a calculator exercise, you can evaluate this definite integral directly on your calculator. You know how to do that now. Maybe you should try that to make sure you get approximately 44.282 gallons. Remember, this represents gallons. All right. And we have to round or truncate to 3 decimal places. We're saying it's approximately because this is going to be a very large irrational number. I believe it's an irrational number. So maybe it's not irrational, but it's going to have more decimals than just 3. So that's why we say approximately. All right. So what does all that mean? Well, if we want to find the average rate of pollutant leaked from the tank from 4 to 10, right? Not how much it happens each day, but over the course of days 4 to 10, on average, how many pollutants are leaked from the tank? This is where we use our average value function. So we take the integral from 4 to 10 of r of t dt, and we're going to divide it by 10 minus 4. Or we take 1 over 10 minus 4 times the definite integral from 4 to 10 of r of t dt. We already got the definite integral to be 44.282. We divide it by 6 because there are 6 days from 4 to 10. And we get an average of 7.38 gallons per day. That doesn't mean 7.38 gallons per day every single day. Some days we'll have more, some days we'll have less. But on average, over the course of 6 days, it's going to be 7.38 gallons every single day. And that's the way this all works. Now, you're going to go and... My fault, I just hit the wrong button. You're going to go to activity 4.4.4, which is my all-time favorite activity in this active calculus series, and I hope you appreciate it as much as I do. I want you to read through it carefully. I want you to look at the units that they're given. I want you to figure out which is the derivative function, which is the original function. Answer the questions as they're being asked. Answer the questions as they're being asked and finish up this activity. Good luck to you.